Okay, so once you have a pretty good grasp of the concept of Thevenin equivalent circuits, you can start to dabble in maximum power transfer. The basic gist of this is that we have a circuit, similar to the Thevenin equivalence of just a source voltage and a source resistance, and we are trying to maximize the power that is dissipated by this load resistor. So there are a couple things to consider here. First, let's just solve for the power in terms of these three variables. So we have the current through the resistor, the voltage across it. We're to define those right there. Because of Ohm's law, we know that the voltage is just equal to the current times the resistance. So we get this here. Solving for the current in terms of these variables, we get I is equal to the voltage divided by the total resistance, Rs plus RL, and plugging that into our equation over here, we get this final power equation. So this is the power dissipated by our load resistor in terms of Vs, Rs, and RL. So since there are three variables, there are three different cases that we need to worry about. Whenever Vs is our independent variable, whenever Vs is moving around, you can see that it is on top of the fraction and it is being squared. So this is a quadratic relationship right here. So if we have control over our source voltage and we want as much power as possible, all we have to do is just give it as much voltage as possible, and it'll go up with a squared relationship. The next case is if Rs is our independent variable. We can see Rs is at the bottom of the fraction right here. So that means increasing Rs will decrease the power. So in general, we want our source resistance to be as small as possible, ideally as close to 0 as possible, because that is where our power will be maximized. The last and most interesting case is when the load resistance is our independent variable. So that's when we're changing our load right here, which is also the most common use case. As you can see, our load resistance is both at the bottom of the fraction and being multiplied by the entire thing. So this creates a unique shaped function where it tends towards 0 on each side, but at the middle, where RL is equal to Rs, we have a local maximum. So we are trying to find, for all the circuits that we're going to be doing, we are trying to set our load resistance to be equal to our source resistance, because we know at that point we will have the maximum power transfer to our load. So let's go ahead and jump into some examples. Okay, so here's our first problem. We see right off the bat that Rs is going to be a constant, so we're not going to be able to manipulate that. And instead, what we do have control over is R. So we want to find the value of these R's in this equation such that maximum power is transferred to this load circuit here. So in order to do that, we need to find the equivalent resistance of the load circuit in terms of this R variable. That may sound weird at first, but if we look at this just right off the bat, we can tell that these two resistors are in parallel. So we can combine them to one resistor. And since they were both 2R, then this new one will just be R. The two resistors in parallel combined to one with half the resistance. Now you'll see that these two are now in series. So we add them together to one resistor. The resulting resistor is just 2R. So this is the equivalent resistance of our load circuit, RL. So we want to set RL equal to RS in order for maximum power to get transferred to our load. So we get 2R is equal to 100 ohms. And dividing over, we get R is equal to 50 ohms. So that is our answer. Not too bad at all. We know that when R is equal to 50 ohms, we will have maximum power transferred to our load. Okay, so this next example is much more complicated, but it's still the same process that we're going to go through. We have our load circuit here, and we're trying to find the Thevenin resistance of that load circuit in terms of R. And once we do that, we need to find the value of R that will maximize the power transfer, and that is the value of R that will make the equivalent resistance equal to our source resistance over here. So we have some dependent sources in this thing, but no independent sources. So the best method to do this would be external source method. I'm going to use a voltage source because that'll clear up some of these variables here. Set it to 1 volt, and remember, we cut off our source when we're just finding the Thevenin resistance of our load. So let's go ahead, set this to ground. That means this node will have a voltage of 1 volt, and in order to find the Thevenin resistance, we are trying to find the current, we'll call it IS, that is leaving our source. So if we draw all the other currents in this node, we'll see that IS is equal to I1 plus I2 plus I3. We know, let's write out an equation real quick. We know that this I1 will just be 1 volt minus 0 divided by R. So I'll put 1 over R. For this next current, I2, we don't know the voltage at this point, but it's connected directly to a dependent source, which, okay, this dependent source is dependent on Vx, and if we look at where Vx is, it's right connected to this 1 volt source. So we know Vx is equal to 1 volt, which means this dependent source is outputting 1/2 of a volt. And since it's connected directly from ground, raising us up that 1/2 volt to this node here, we know this node is 1/2 volt. So we get 1 minus 1/2 divided by R for our second current. And for this last current, we have another unknown voltage at this point here. So it doesn't look like there's any shortcuts for this one. We're just going to have to do node voltage analysis. So we'll call this one V1 and this one V2. And let's go ahead and put 1 minus V1 over R in our equation. Okay, so now we want to find V1 in terms of R. We don't want any other variables besides our current and R. So our next goal is to find V1 in terms of R. So let's go ahead and do that. We're going to have to use node voltage analysis. So we have 3 currents going out from here. This middle one, 1/4 Vx. We know Vx is just 1, so that would be 1 quarter of an amp, so 1/4. And then this next current going out here, V1 minus 1 over R. And then the final one is V1 minus V2 over R. That's all equal to 0. I can get this out of the way. Okay, now for our V2 equation, I'll go here, V2 minus V1 over R plus V2 minus a half over R plus V2 minus 0. So V2 over R. All that equals to 0. Just looking at this, it's messy and we only have 2 equations. So I'm going to do substitution to solve this system. So I like the look of this one. I'm going to go ahead and multiply it all by R. I get V2 minus V1 plus V2 minus 1/2 plus V2 equals to 0. We have 3 V2s, and that is equal to, bring our V1 and our half over. So we get V2 is equal to 1/3 V1 plus 1/6. Okay, we're gonna have to bring it back up here to plug into our equation. We get 1/4 plus V1 minus 1 over R plus V1 minus V2. Plugging it in, we get 1/3 V1 plus 1/6. All that over R. I think again, we'll just multiply by R. We get R over 4 plus V1 minus 1 plus V1 minus 1/3 V1 minus 1/6. If we combine our like terms, we get 2 V1 minus 1/3 V1. So that's 6/3 minus 1/3, 5/3 V1. We have minus 1 and minus 1/6. So I'm going to go ahead and bring that over here. So 6/6 plus 1/6 is 7/6. And then minus R over 4. I'm going to keep track of that. Then we just multiply everything by 3/5. We get V1 is equal to 21/30, which simplifies to 7/10 minus 3R over 20. So now we have our V1 in terms of R. We can bring that back up to the top here. We'll go IS is equal to, you know what I'm going to do? I'm going to multiply by R first. So IS R is equal to 1 plus 1 minus 1/2 plus 1 minus V1, which is 7/10 minus 3R over 20. That's a lot nicer to look at. Okay, so combining everything, we get 3 minus 1/2, so that's 5/2 minus 7/10 plus 3r over 20. 5 halves and 7/10. So 5 halves would go to 25/10. 25 minus 7 is 18/10 plus 3r over 20, and that is all equal to is times r. If we divide r back over, we get is is equal to 18 over 10r plus 3/20. Okay, so now we know the current being used up by our external source. If we want to find the Thevenin resistance, we know that is just the voltage of our source, which is 1 volt, divided by the current. So we have 1 over 18 over 10r plus 3/20. I'm going to multiply everything. Oh, no. Not quite yet. No, we'll go ahead and do it. 20r, just to simplify. And we'll get, oh wow, 20r over 36 plus 3r. That is our Thevenin resistance. Okay, we have our Thevenin resistance. Now we set it equal to our source resistance, which is 4. And we solve for r. So going ahead and doing that, we multiply both sides by 36 plus 3r. We get 20r is equal to 4 times 36. Oh, jeez. That wasn't in the multiplication tables. 144. That's not terrible. Plus 3r times 4, 12r. Bring our r over, we get 8r is equal to 144. Divide by 8, we get r is equal to 18 ohms. And this is our final answer for what r is. So now we know when r is equal to 18 ohms, the Thevenin resistance of this entire load circuit will be equal to 4 ohms, which means there will be maximum power transferred into the load. So going ahead and doing this last part of the question, if the source voltage is 8, how much power is the load circuit dissipating? We can go ahead and rewrite the Thevenin equivalent that we just found. So we have our source, which we know is 8. Our source resistance is 4. And we found when R equals 18, the load resistance can also equal 4. So finding the current through here, we have I is equal to 8 divided by 4 plus 4, which is just 1 amp. And if we remember our power equation, power through RL would just be equal to I squared, so 1 squared times the resistance of RL, which is 4. So our load circuit is dissipating 4 watts. Alrighty. That's that.